and there's still a lot of things to be discussed. You remember you were not there last week, we talked about the isotopic composition, and we could identify some end members or some mantle, different mantle sources, and we will continue with that today. We will first look at one isotopic system in more detail, that is the lead isotopes, because it's really interesting, the findings on lead isotopes and the conclusions about the mantle evolution and mantle composition. And then in the second part of this lecture, we will look at the models, at the models how the mantle works. And there's a lot of research going on at the moment, because there are different results from the geochemists and from the seismologists and from the geophysicists, and it's really tricky to put all these different findings into one model. So at the present time we have different models of how the mantle works, and I will show you the most important ones of these. But let's start with the uranium lead system, or with the geology of lead. So actually what we can see here is that we have three different radioactive isotopes, which all produce different lead isotopes. There's two uraniums produce two different leads, and one thorium produces another lead. This you could call the uranogenic lead, this you could call the thorogenic lead. And these three radioactive nuclides, they have different half-lives. That's also very important. We have a half-life of uranium-238, which is more or less in the range of the Earth, the age of the Earth. Half-life of 235 is much lower, only 700 million years. And the half-life of thorium is the longest from all these three. So we have different production rates of these three lead isotopes. And we have one isotope of lead which is not produced by radioactive decay. That is a stable, it's a reference isotope, or a stable or unradiogenic or non-radiogenic isotopes, the 204. So we have these four isotopes. And the ratio of the 206, 204, 207, 204, and 208, 204, they change with time due to the decay, but the change rate differs because of the different half-lives of the three isotopes. So that is how you can explain the increase, for instance, of these ratios is due to the decay of the radioactive parent isotope. And how that looks, how the change of the isotopic ratios with time, how that looks, that can be displayed in a diagram. And that is this diagram, also called lead evolution diagram here, which shows the increase of, in this case, the two lead isotopes are from the decay of uranium, from uranium-238, from uranium-235, and you see this is an evolution of these ratios for different mu ratios. This is a term used for the uranium-238. This is generally known as mu. Over lead 204. So it's actually an isotopic ratio, but this ratio defines the velocity of growth. When you have more uranium 238 and less lead, then you can produce more radiogenic lead isotope ratios. So these lines here are for different mu values. The mu value is here shown as 5, 6, up to 10. And if we consider a simple one-stage model, the one-stage model means we start with the lead isotope grow when the Earth was formed, yeah, and that lead isotope composition here, in German it's called Urblei, we call it initial lead isotope composition, that can be measured on, for instance, on iron meteorites, yeah, on meteorites which don't have uranium, like the one which is used. It's a meteorite from the Canyon Diabolo. That one is used as reference for the initial lead isotope composition of the Earth. And then you can calculate for various mu values the grow lines, and these are shown here. And when you do that over the whole history of the Earth, you end up at present day at this line. And this line is called the geochron. Yeah? It would be the present day isotopic ratios for lead, which evolved in different reservoirs or with different mu ratios, with different uranium-lead ratios. So that would be the story. You can easily calculate these ratios here from simple equations, which include the decay constant of the different uranium isotopes, and the ratio of the two uranium isotopes is given by this value. And then you could calculate these curves. And this model actually is known as the Holmes-Houtermans model. And yeah, what you can do next is you could look at some lead minerals like galena. Galena is a common lead mineral in the Earth crust, and you could measure the lead isotope ratios in galena. That was done in the 1970s, 1980s by many geologists all over the world. And it was found that the lead ratios of the galena, at least of very young galena minerals, plot to the right of the geochron. That was an unexpected finding. Yeah, they plot in a field actually where the lead isotopes should not grow. Even when you have very high mu value, you would not get a sample to the right of the geochron with a one-stage model, because this is a one-stage model. Yeah, we look at the given mu over a given time. So obviously one-stage model doesn't work, and the next step was that the people looked for alternative models, and a very famous model is that from Stacy and Kramers, and that contributes to a change of the mu value somewhere in the early history, around 3.7 GA, somewhere around that. That is because here we are looking at the lead isotope evolution of the mantle, and we know that already in the Archean crust was created. So the mantle has changed, and that could have caused a change or an increase in the mu value. And that is actually considered in the Stacy and Kramer two-step model. Maybe let me just. This is a model to what I said. Here is the Stacy and Kramers model, which shows that at about 3.7 GA in the past, the mu value changed. Initially, we had a mu value of around 7, and then at this time, we changed it to higher values due to fractionation process and crust building processes. The mu value in the mantle get higher, around 10. And then when you start here calculating with a mu value of 10, then you come up with a line which extends to the right of the geochron. Yeah? And that would be the Stacy and Kramers evolution line. That is actually, this lead evolution line is also used by geochronologists for correcting their samples for common lead. But this is actually a two-stage history model. I jumped over this one. This is just another example for the Holmes-Houtermans model, which shows you a point here, point P. You could measure, for instance, this lead isotope composition in a galena. What do you think? How would you interpret that? If you have a lead isotope composition similar to that on point P, yeah, you would have a growth over a considerable long time, and then here you have the formation of galena, and that means you have a pure lead mineral. Galena is a pure lead mineral, and then the lead isotopes stop to grow. They cannot grow anymore because there's only lead and no uranium in the mineral. And when you measure a point like this, you could say that your galena mineral has formed maybe 3 billion years ago. If you would have a uniform lead isotope growth history. So that was what the people used, the lead-lead diagram in the 1970s, 1980s. They looked at the galenas. They had enough enough lead in the mineral. And then they found, oh, there are so many galenas plotting to the right of the geochron. And then the Stacy and Kramer model was proposed in the end of the 1970s. And then also the people started to look on mantle rocks, on basals, on morbs, or on OIBs. These are more difficult to measure because they have lower lead concentration as galenas, but nowadays we have a lot of lead isotope data also from basaltic rocks, from ocean islands or from mid-ocean ridges, and these are shown here. This is the summary of the rocks we were looking so far in the lecture: OIBs, global OIBs, and global morbs. And what we see is that they almost all plot to the right of the geochron. Yeah, so when so many rocks plot to the right of the geochron, actually we have to ask, is there another reservoir with less radiogenic lead, which must plot to the left of the geochron? This is shown here by missing reservoir. That is one question which comes from this data distribution. Another interesting point is actually that the data from the mantle, they are very similar to average continental crust. That is the green square here. And that is very interesting. We have seen that in all other isotopic systems, the crust and the mantle are very different. But that is not true for the lead isotopic system. The lead behaves anomalous. Yeah? We have the same composition for the crust as we find in mantle rocks. So they are the same in isotope composition, although they are actually complementary in the lead concentration. Yeah? There's the crust has a very high lead concentration, whereas the mantle is very much depleted in lead. So they are very different in terms of the concentration, but very similar in terms of the isotope composition. That is unique amongst the isotopic system, and that is related to the anomalous behavior of lead. Because when lead, or when material is subducted, the lead that is what is believed, is transported by fluids into the melt and gets enriched in the continental crust. That's why the continental crust has positive lead anomaly. And the same behavior actually is for uranium. So we have both high uranium and high lead in the continental crust, whereas normal magmatic melting would only enrich uranium in the melt. And then the melt and the crust would have a high uranium-lead ratio. But due to the release of fluids at subduction zones, lead is also enriched in the continental crust, and that results actually in the same isotope ratios in the crust and in the mantle. That is one point. But the other point, and that is called actually as a first terrestrial lead isotope paradox, or lead isotope paradox, is that almost all rocks plot to the right of the geochron. And if they do that, there must be some other reservoir which we have not yet found so far. And there are little data, or actually from rocks which plot to the left. There are some from the EM1 component we see later. They plot here. These are maybe some EM1 OIB basals. There are some lower crustal rocks on old cratons which have a depleted lead isotope composition, but most plot to the right. And that is what many people are thinking, the reason for that. No? I come back to that point. First, we can have a look on this group. These are OIBs which have extremely high radiogenic lead. And we already talked about that last week. That was the high mu component, yeah? Which is characterized by very radiogenic lead composition. More radiogenic than you can have in a normal mantle rocks. And I want to show you this distribution again. So we leave this lead evolution diagram for a moment. This is just some more detailed view on the data. This is a geochron. Here are all the ocean islands. Yeah, most of them lie to the right of the geochron. Yeah, we call it the first terrestrial lead isotope paradox, or simply lead isotope paradox. And when we use the isotope diagrams, strontium against neodymium, or lead against lead, or mixing neodymium with lead or strontium with lead, then we can identify the different end members. This we did already last week. Here, when we add the lead isotopes, we can more clearly see the high mu component. Yeah? High mu, again, this is mu, high uranium lead, produces over considerable time, that what one also needs because of the long decay constant, very radiogenic lead isotope ratios. So when you use the different diagrams, you can discriminate these sources. Here's the high mu is very nicely seen in these diagrams. When you use the strontium, like here or here, you can see the EM2 seems to be a special mantle component. That component actually requires very high rubidium strontium because it's the highest strontium ratios. It has the highest strontium ratios, higher than those which could be produced in the normal mantle. So this high ratio must come somehow from, yeah, I could ask you, what do you think? How do we get the radiogenic strontium signature in the OIBs? From which reservoir? Sure, I think you know. Which reservoir has high strontium? Huh? Yeah, but where does it occur? The plagioclase, and which part of the world or crust does it occur?
You're looking for depleted or undepleted?
Maybe, well, not depleted or undepleted, actually enriched reservoir. That is the crust. It's the continental crust. Your granites, they have high strontium ratios. It could be lower crust or upper crust, yeah. But the continental crust in both parts actually, they have quite high strontium. So this strontium ratio can only be produced by the subduction of material which comes from the crust, but not from the oceanic crust, from the continental crust. Yeah, it could be sediments which are derived from the continental crust, or it could be some part from deeper crust which might get delaminated in the mantle. But the most likely reason would be sedimentary material. So the high mu component we have not discussed. What could be a potential source for high mu? That maybe is more difficult. How can we produce high mu ratios? First, why in sediment?
Sediment is enriched by lead.
Is enriched in lead. Yeah, but here we must have a high uranium-lead ratio. Yeah? And that over a considerable long time. And we are looking for sources with a high mu ratio over a long time. And one possible source would be the oceanic crust. The oceanic crust, when it goes through the subduction zone, because then the lead gets released by the fluids, yeah, due to dehydration, and then we would increase the uranium-lead ratio, or by ocean floor alteration. This could also happen. Yeah, so altered oceanic crust. Altered oceanic crust could also, we can see here the high mu component, for instance, in the strontium diagram. The high mu component has a very low strontium ratio, very low strontium, that also would fit with oceanic crust. Yeah? That is what is generally thought, which produces the high mu subducted oceanic crust. So we have subducted oceanic crust, probably we have continental crust, and here the EM1 source. You have to look at various diagrams to find some special characteristic. When you look on all these, maybe it's more difficult. When you look at this one here we have the thorogenic lead against the uraniogenic lead, and that gives you, it is the 208 lead over the 206 lead, and this is equivalent to the thorium-uranium elemental ratio, yeah? Because this is produced by thorium, this produced by uranium. And so we have high ratios here that we're looking for rocks or reservoirs with a high thorium-uranium ratio. And one possible source for that would be some pelagic sediments on the deep ocean floor. They have those characteristics. Or another potential source would be the deep crust, which is highly metamorphosed, which could also have much higher thorium than uranium. But most people prefer that these could be pelagic sediments. So we have explanations for all these, and we already discussed about the DM, which is the source is a depleted mantle. So we could summarize that and give an overview about the mantle reservoirs. Sometimes it's also called flavors. No? Flavors is because some of these isotopic features are only found in individual plumes. Yeah? So that might be only a flavor. Yeah? It is only seen on one or two different places. But when you look across all the rocks presently analyzed, then you come up with, you could say, at least 3 reservoirs, including the depleted mantle. Then we would have 4 reservoirs. So the high mu, the radiogenic lead reservoir, most likely recycled oceanic crust. During that also rubidium can get lost, and then we would not increase the strontium ratios very much, even over a very long time. And when it loses rubidium, then we have a high mu value, and when we can produce over a long time, we still need time scales in the order of 1 to 2 billion years to produce these features, yeah, because of the long half-life of uranium. That means also the slabs must be stored somewhere in the mantle. They cannot get subducted and immediately melted and feed it into the plume. There must be a considerable long residence time for this material in the mantle. EM1, yeah, we said pelagic sediments, maybe subcontinental lithosphere. It's a complicated topic actually. How big is the contribution of the subcontinental lithosphere in mantle geochemistry? We can't see that really well, but we know there is some Sometimes there is delamination of lower crust, and this lower crust could feed the mantle and could give rise to special elemental or isotope characteristics. But it seems more likely that signature is derived by sediments, because these sediments exist on top of the ocean crust, and in many subduction zones they get subducted. And EM2 component, unique in that it has the high strontium ratio, and the only reservoir which can explain that is a continental crust, or the sediments derived from it. So these are the contributions of material into the mantle. And yeah, at the end we will look at the model of how the mantle looks like, now where we may find all this material. But before we do that, let me continue with the lead story. We were talking about the lead evolution, and we found that most of the OIBs and MORBs plot to the right of the geochron. So the people of a long time were looking for explanations for that. And one explanation which really could explain this isotopic feature very well would be that the lead would have entered the Earth's core, because then it's not available, and then we would get a high mu. And that model was suggested by Jean-Claude Allègre. We already talked about him. This is his paper 1982. It's called the core pumping model. Yeah, maybe core is siderophile at that temperatures or pressures. It's not really well known. It's also a volatile element, actually. And but this theory hold for a long time, and then after that, other people did some experiments to see, to try to prove it or not. And this one study from Newsom here, they tried to find a correlation between lead or the mu value and other siderophile elements like molybdenum. This is molybdenum. Actually, it's normalized against the lithophile element promethium, and actually, what is expected if the core, if the lead has gone in the core, that there should be a correlation between the mu value and other siderophile elements or element ratios, and this correlation should be positive, but it cannot be seen any positive correlation. And that was the first big argument against Allègre's core pumping model. Yeah. But that is then the problem continued, and still not really clear yet what happened with the lead, or why do all the samples plot to the right of the geochron. There's another paper from Lagos et al. Published a few years ago. Yeah, they had another theory. They said that the lead was lost not in the core, it was lost actually in the space during the giant impact. Because the giant impact happened just 50 million years or so after the core was formed. That means that led to the formation of the moon, and that impact could have caused volatilization of the lead, because lead is quite volatile, and it could have taken the lead away from the Earth around 4.5 GA ago, and that would fit. That would mean that the Earth would have acquired a high mu value already very early, yeah, just 50 or 100 million years after its formation, and then we would get the higher lead isotope ratios. Well, probably something like that could be feasible. Huh?
But wouldn't you see the same pattern then for other elements that would have been volatile?
Yeah, we see. The Earth has lost its volatile elements. Yeah. Has lost its volatile elements. It also has lost its semi-volatile elements. Yeah.
So you don't see this only at
You can say, you can say so. The question is the reason for that. Maybe the volatile elements were lost during a phase of strong solar activity. Yeah? Actually also during the formation of the sun. That is why the inner planets actually are very poor or very depleted in volatile elements. But this model for lead, together with a giant impact, is new. But it is very well elaborated in this paper. Yeah. Other papers say they discussed it could be a reservoir for lead, could be the lower crust, subcontinental lithosphere. There are some samples, yeah, which plot here, but probably is not enough to compensate all these data which are right to the geochron. Even some people thought that the age of the Earth is wrong, and that means then the geochron would shift. If you would take another, this geochron is calculated for 4.53. If you calculate another, actually the accepted age of the Earth is 4.56, but if you calculate for 4.56, it would lie here, somewhere here. So a younger age would shift it a little bit to the right, but it also cannot explain. And the age of the Earth is well documented, yeah. So I think we should not change that value, and it must have some other reason. So probably the loss of lead could be very likely. And if we still really have a hidden reservoir somewhere in the mantle or somewhere in crustal rock, this is also highly questionable. As I said, we have some rocks, some lower crustal rocks, which have these lead isotope ratios, but this cannot explain, cannot mass balance actually, you know, all the data points on the right of the geochron. So this point I already discussed now, that we see very different lead concentrations in the crust and in the mantle, but very similar isotope composition. And that is due to the anomalous behavior of lead. Yeah? Because it's transported so easy in fluids. So we will not leave this the lead story. We will come to a final point, and that is maybe the most complicated topic of this talk today, but I will just briefly explain it and try to do it as easy as possible. And this has to do something with this ratio here. We will look at this ratio, which is called kappa. And the story is about the kappa conundrum, because there's also, like with a normal lead evolution, something which looks really strange. And what we actually do is we look at the radiogenic lead ratios. This is something indicated by the asterisk. This means this is a radiogenic lead. This is a lead produced by the thorium. This is a lead produced by the uranium. We also have some common lead component, yeah. But you can calculate the radiogenic component, which is produced for a given thorium or uranium, simply with this equation here. Yeah, this gives you the lead isotope composition at the present day minus the lead isotope composition of this is cap T, that is the time of the, for instance, for the Earth's formation, and the difference here gives you the ingrowth of radiogenic lead, and this is for 208 and this is for 206. So this actually corresponds to the thorium uranium. Yeah? And when we look in the mantle over whole time, it was found that the 208-206 ratio, or the kappa value, is actually around 4. Roughly around 4. Now maybe it could be 3.9. It could also change a little from 4.1 to 3.9. There is a little trend, but we don't care about that. We just assume it is close to 4. this ratio, this kappa. Kappa, again, measured by 208, 206 lead, and from the kappa we can calculate the thorium-uranium ratio. So the surprising thing that is shown here, this was a famous study from Gaylor and O'Niens. What they did is they measured this ratio in MORPS. No? So we are looking at MORPS, it's an upper mantle system, and they found that the kappa ratio in MORPS is around 3.8 or 3.7. Yeah, this is a thorium-lead ratio derived from the 208-206 lead data. And the interesting point is that you can also measure the thorium-uranium ratio directly, yeah, in a MORP. You can just look at the elements, measure not the isotopes, the lead isotopes, you measure the thorium and the uranium. And when you do that, you will find a thorium-uranium which is at 2.5. So this is here, it's shown here. And this is actually what is called as a kappa conundrum. And the ratio, which is this ratio, the thorium-uranium ratio, which is measured directly, we call it the instantaneous thorium-uranium. Instantaneous because this is a thorium-uranium which is in the MORPS which are currently sampled. But the other ratio, the kappa, measured over the lead-lead, gives you a different information. What kind of information? You get a time integrated or time averaged information. Yeah? Because these ratios grow over the time depending on the thorium-uranium. That simply says, this 2.5 is not shown in this diagram. This is just said here. So this is what you measure in MORPS, a thorium-uranium element ratio of 2.5. When you use the lead isotopes, then you get a ratio of 3.7. Yeah? It's also an indication for the thorium-lead. But the first one is the instantaneous value. The second one is a time averaged value. I hope you can understand. Time average value. We said that the isotope ratios need time to evolve, yeah? And depending on the reservoir. So that means that obviously the time integrated value demand another reservoir than the present day MORP. The present day MORP reservoir is a depleted mantle, but this kappa ratio tells you that that system is actually an open system, yeah? And some other material is transported in this reservoir, maybe from the lower mantle, which has another kappa value. And when you can even go further and look at the kappa ratio of the Earth, which is around about 4. It has a little bit an error of 0.1, but when you use this value and you try how long it takes to get the kappa value measured in MORP, then that would give you an average residence time of the MORP source of around 600 million years. Yeah, that means every 600 million years the MORP source is replaced by other material. That is what the time integrated lead isotope ratios tell you. And anyway, we have this fractionation in that source, and that fractionation immediately, melting of that mantle, immediately changes the elemental ratio into a thorium-uranium of 2.5. But it cannot change the isotopic ratio. Now, the isotopic ratio cannot change by that process. Yeah, and from this we learned that the systems are open, that we are not dealing with a mantle which is continuously depleted, we are dealing with a mantle which is also replaced by material from the lower mantle. And then later we will look at the models. And then, for instance, when we look at the Berkovici and Carato model, it just can account for this observation. Okay, now the last point about lead. We are not finished with it. We must run a little bit quick through these figures, but it's not a new figure. It's always the same. The lead evolution diagram. Here we have the geochron. Here we have all the ocean islands, which plot on the right of the geochron. And this is from work from Stan Hart. He looked in more detail and in the geographic distribution, and he found that OIBs from the northern hemisphere, they are on a line. And he called this a northern hemisphere line, or the northern hemisphere reference line. And then he found some ocean islands, mainly in the southern hemisphere, which plot on top of this line. Yeah? And this one he called the Dupal group. This is in honor of Dupré and Allègre. That's the mixture of their names. And the Dupal group deviates from the northern hemisphere line, and when you look on a more global scale, you can find these Dupal anomaly here around South Africa in a larger dimension. And we have a second anomaly. It's called the Zopita anomaly, or South Pacific isotopic and thermal anomaly. That's in the Pacific Ocean, or actually in the whole Pacific area here. So these these are also connected with enriched mantle features with EM1 or EM2. So these are large anomalies they are found, and it seems there are some large mantle anomalies. Yeah, that means that the mantle on a big scale is not homogeneous. That's a picture from with a very low resolution actually. No? We can now look in a more detailed resolution when we use other methods like tomography or seismic scattering. But anyway, this is from lead isotopes, and it just gives you the information of some large-scale deviation in the composition of the mantle. Dupal and Zopita. Yeah, and then this is the last point before we come to the models. You can plot the isotope data in a tetrahedra, like is shown here, where because we said we have actually 4 end members, so a 2-dimensional diagram like I showed you doesn't work. It's at least a single one. So you can use presentation like this with the EM1, EM2, depleted mantle and high mu, and then you end up with some alignments here. These are in these tubes. There are many samples, yeah, all available samples from the ocean islands, and you see that there is some trend to a point which is called foci, or focal zone. We mentioned that also last week. So the question here is now, do we have a 5th component in the mantle, which is common in all plume material, yeah? Something, a mixing end member which you can see in all different plumes. It seems so, no? The plumes which generate EM1, plumes generate EM2, and so on, they seem all to contain this foci component, foci for focal zone. It's a less depleted mantle composition. Whether it is really a primitive mantle, it is not exactly has not exactly the same characteristics as a primitive mantle, but it is closer to the primitive composition than all other components shown here. So this is a famous mantle isotope tetrahedron. And yeah, then we can come to the final point. And maybe the most interesting part, because we look now at the model, or what the geochemists and or geologists actually think about how the mantle looks like, how it works, the mantle geodynamics. If there is a layered mantle, if we have maybe a whole mantle convection, or if we have double layers in the upper mantle or in the lower mantle. Actually, when we look at the recent models here, we can say that it is quite unclear. A.L. Hoffman, he just recently wrote that the mantle dynamics is in a state of turmoil, and that is because we have different results from the geochemistry and from the seismology and from the geophysics. And that causes a little bit trouble at the moment. Rollison in his textbook here, he writes that the view of the mantle is in a state of transition. So that's why there are many new models at the moment, but it's unclear which model is really the true model for the mantle. That is because originally, let me see, now that comes, originally it was thought that there is a depleted upper mantle and a non-depleted lower mantle, and they are both separate. But then it was shown, it was mainly due to mantle tomography, that the subducting slabs penetrate the 660 km discontinuity and go down into the deeper mantle. And that gave rise that some people said there must be only one layer convection if so much material goes in the deeper mantle. Yeah, and then it's the picture start to change. So first we will look at some evidence. Now, what are the pros and what are the cons for a geochemical layering? Means maybe two mantle layering. What are arguments for whole mantle convection? One point we have already considered, I already showed you this figure. It shows that the transition, the phase, and that is the phase where ringwoodite goes into perovskite. That this phase transition has a negative Clapeyron slope. Yeah? Negative Clapeyron slope that is equivalent to this picture, and that would prohibit that the slab would penetrate this phase transition so easily. That is shown by this arrow. I can show you the phase diagram here. You see, these are the phase transitions for the mantle mineral. We have the olivine in the wachsleite transition, wachsleite in ringwoodite. Ringwoodite in perovskite is a negative Clapeyron slope, and that is a big argument to say that the slabs cannot so easily penetrate into the lower mantle. Yeah? Because the phase transition would occur very deep when there is a less dense phase surrounded by denser phases, and that would cause uplift, or at least some floating mechanism of the subducted material, and that would favor a two-layered mantle. Just from this thermodynamic considerations. Then what we did not do so far, we didn't look at the heat transfer and the heat loss. We can get some arguments while looking at the heat transfer. You know that the Earth continuously loses heat. No? This is about 40 or 44 terawatt heat gets lost. 44 terawatt, yeah. And that is due to the cooling of the Earth in one part, and also we also have heat production by the radioactive elements like uranium, potassium, and thorium. They produce, we know roughly the contents or the concentration of these elements in the Earth. They produce roughly about 20 terawatt. So half of the heat which is lost by the Earth is is produced by these elements. Anyway, the Earth over geological time loses the heat. No? This heat production was higher in the past because they have partly decayed, so that source gets lost. But we can measure the heat loss. It's mainly along mid-ocean ridges. We know the concentrations of these elements, and there are some estimates now based on element concentration and the heat loss measurements that the upper mantle actually is very depleted in radioactive elements, and it can only produce 2 to 6 terawatt. That's not very much. We can measure it from the crust, and we measure the whole. The whole loss is 44. That means actually there must be heat-producing elements in the lower part of the Earth, is the equivalent to this number, 32 to 36 terawatt. That's quite a lot, and that is could be an argument for a two-layered mantle. Yeah, that we have a deeper mantle. There must be with a high heat production, and that is separate from the upper mantle. This is how you could interpret it, but geophysicists, they just use another explanation. They said if there is a lower mantle which produces so much heat, then there would be a thermal boundary layer between the lower and the upper mantle, and that layer would be buoyant and would not be thermally stable, and that would cause actually a kind of whole mantle convection or heat transport by advection or convection processes. The first point, when we have a lower mantle with a high heat production, and the heat transfer could be by conduction, that would explain the big difference in the heat production, but obviously that doesn't work by conduction. Then we would get the thermal boundary layer, and that would be unstable. And so anyway, based from the heat flux in the Earth, you could either develop a two-layer mantle or also a one-layer mantle, depending on your arguments. It's not very clear from that alone. Then there is the other argument of a two-layered mantle that is called the argon argument. The argon argument that is based on the calculation of argon by the decay of potassium. We know the potassium decays into argon, and we know how much potassium is in the Earth. I will show you that the calculation later. But we know the potassium, and from that we can calculate how much argon is produced. And actually, we only find 50% of the argon. 50% of the argon in the atmosphere or in the crust. The other 50% is missing, and it cannot escape from the atmosphere because it's too heavy. So the geochemistry, or at least one club, considers that argon is in the lower mantle, and that therefore the lower mantle and the upper mantle they have a different convection. So two-layer mantle model. That would be favored from when you calculate the argon budget. What else can you do? You can look at the isotope data at some extreme ratios like the high mu, or a very extreme and very good example would be the osmium isotopes. Here, this is the isotope ratio of osmium, which is very high on some ocean islands like Hawaii, and such high ratio, the same holds true for lead, for the high mu, can only be explained when the material is aged isotopically. Yeah? That means somewhere in the Earth's mantle there must be some kind of slab graveyard, and where the material can be stored over 1-2 gigayears. And that can only be the case when we have a two-layered mantle. If we have one-layer convection, such aged parts would not be found. Yeah? You need a place where this material can be stored, maybe close to the core mantle boundary or wherever. But this material which comes presently up at Hawaii or other island with such a radiogenic osmium isotope ratio or such a high mu signal must have been in the mantle at least in the order of 1 to 2 gigayears. Yeah? This is just an argument which favors that there are parts of the mantle which do not take part in the convection, which are actually against a whole layered mantle model. Yeah, and then the other point what you can do is you can make some mass balance calculation. This is also interesting to see of how much of the mantle maybe is depleted or how much of the mantle is primitive. So that can be done. It's not quite difficult to reconcile these numbers. This is a concentration of uranium and thorium. They are quite refractory elements. We know these concentration from chondritic data, and so you can use uranium and thorium. Potassium is more difficult, but we have a good idea about the potassium-uranium ratio, and that ratio is around 12,500. And when you have this ratio and you have the uranium concentration, then you can also calculate the potassium content. It's around 250, so it's quite reliable number, with a relatively small error. And then you can use these values for the bulk silica earth. We know them from the continental crust. We have good data set from continental crust. And we can calculate them from the depleted mantle. How do we calculate them from the depleted mantle? We use the MORPs, and we have our models about MORP generation, about 10% partial melting. We know the distribution coefficients of these elements, and then we can come up with a model element concentration for the depleted mantle. And with these values, you can try yourself. You can calculate the fraction of the mantle that is depleted. I did it just last evening to check, and what you have to do is you have to assume that the volume of the continental crust is about 0.5%. That is what we think is a volume of the continental crust, roughly 0.5%, because all these elements are highly enriched in the crust. But that is a volume, yeah, actually 0.5% of the whole Earth is made up of continental crust. And then you have the data for the DM, bulk silicate earth, and then you can calculate the fraction of the depleted mantle. And it is roughly 50%. It's a good, important number. Yeah? We can say roughly half of the mantle is depleted. What does it mean? That means it is more than the upper mantle, because the upper mantle stops at the 660 kilometer discontinuity. So the depleted mantle must be more than only the upper mantle. So when we look at any model, that should consider that. And other calculation you can do, you can just look what happens during 4.5 or 4 billion years of plate tectonics, how much material gets subducted. Presently, it's, the volume is about 18 square kilometer per year, but that is oceanic crust and lithosphere. That is the volume of material which is subducted each year, 18 square kilometers. Cubic, sorry. Wouldn't make sense otherwise. And when you calculate that for over a period of 4 billion years, you come up with these numbers. That could be 5% of oceanic crust subducted into the mantle, 5%. Only 2.3% oceanic crust. Yeah? And the remaining almost 50% would be the lithosphere. actually depleted. That is the material below the oceanic crust, which is depleted. They call it the sterile mantle. But that is a mantle which has been processed through the subduction zone. So this is also 50%. That means we have 50% depleted mantle, 50% recycled mantle. That means the whole mantle has changed. Yeah? The whole mantle somehow has changed. It has been either depleted due to melt extraction or re-enriched. Or some sterile material has been added. So what about the primitive mantle sources? What about how can we explain the noble gas isotope signatures? That's very difficult, no? Because maybe all the mantle has reprocessed somehow based on these calculations. But that is what is also general consensus, that then there may be only very little really primitive mantle, if at all. And helium isotope signatures on neon must be explained somehow different. Maybe that is mantle, very old mantle, yeah, which has developed such signature. Okay, now we are at the point where we can talk about the mantle models. We still have 20 minutes, I think, yeah? That should fit. So to make it not so complicated, I divided these models in two broad parts. It's actually the layered or layer cake model, which means that the mantle should be somehow geochemically stratified, yeah, have layers with different geochemical composition. And the so-called plum pudding model. The plum pudding model, we only show you one example at the end, which considers a mantle as a pudding in which plums are located, and these plums represent enriched material, yeah, the enriched reservoirs. That is what we basically can divide it. Now we start with the layering models. Actually, this is a very old model before we had any data from MORP or from OIB. Without data, the thinking was like that there is a mantle below the crust which has a convection cell, yeah? And the material is transported by convection. But that model changed after the data from MORP disappeared. Then it was seen that there's a depleted mantle, and it was thought that the MORPs come from the depleted mantle and the OIBs must come from another mantle, and that mantle worked somehow independent from the upper mantle, and that gave rise to the two-layer mantle model. Here's again, Hofmann considers the different types there are. When you have these two models, actually there are still different treatments with the plumes, where the plume material can come from. This is actually more or less a two-layered model, yeah, with different convection in the upper mantle and the lower mantle. The question is where do the plumes come from? Yeah. In this model, they come from the lower part of the upper mantle, and maybe here the lower mantle is leaking here and supplies some material into the plume, but the plume mainly gets material from remelting of the subducted material, which is only subducted to the 660 kilometer discontinuity. So this is a model which you have good arguments for this model, but you also have arguments for a model like this, the whole mantle convection. We have a higher degree of depleted mantle, yeah, roughly 50%, so that's why this brown color goes deeper into the upper part of the lower mantle. And here we have the subduction, the subducting slabs going down right down to the D double prime, and they can be stored here, and then the material close to the D double prime gets incorporated into the plume material after some time of residence. So this is just general, but anyway, we have both is actually type layer cake model. Yeah, we have some layering. Here we have the convection, two types of convection and layering, and also here we have some kind of layering, more depleted mantle in the upper part and enriched or primitive mantle in the lower part. Here's a model which was called MOMO model. It's also Hoffman was contributed or was developed that model. It says that it can change, that there could be phases during Earth history where we have two-layer mantle convection, and during major orogenies, for instance, we could have an overturn of material in the mantle, and then whole mantle convection could take place. For instance, during the Cretaceous. During the Cretaceous, we have no shift in the geomagnetic field for many tens of million years. That could be a MOMO phase at that time. There we have the formation of the lips during the Cretaceous, and huge lips like we see at that time span could be created during such an episode. Well, this is just one more model, and a more recent model which accounts for mass balancing, which also accounts maybe for the lack of chemical stratification. Here at the 660 kilometer discontinuity is the model from Kellogg. Still the layer cake, because we have two layers. We have a depleted upper mantle and a depleted upper part of the lower mantle. This is simply a phase transition. This is generally believed now. Yeah, the 660 kilometer, or between 440 and 660, we only have phase transitions. They are isochemical. Yeah, if there's a depletion, the depletion of the mantle, the depletion of the mantle continues much beyond that discontinuity, as we have seen from the mass balance calculation. So this model further assumes that the slabs get deeply subducted, and then we have this layer here. You see this layer in average around 1,600 kilometer depth, and that layer is not seen seismically. Why? It's not that a change in density at this layer. It is a compositional change, yes. But this material, the denser material, is very hot. It is heated from the core, and it is buoyant, so that then it is less dense, and there is no density contrast. That's right. No density contrast. We don't see that. This is just a speculation from the model, but that would account for the mass balance calculation, that this part is depleted. Here we still have another reservoir which can contain undepleted material, which can contain material which is enriched from this subduction. And from here we can also get the plumes. Here in the very hottest part, these are the coldest parts here. Yeah. There the surface is quite close to the D double prime, where the cold material comes down, and here heat flow due to the core would give rise to thermal anomalies, and from those the plumes could start, and they could take up the material here, which could be, it could be ancient subducted material or primitive mantle or whatever, which gives rise to the different OIB signatures. So this is, it's called the lava lamp model. Yeah, the name comes from a household curiosity in the 1960s, the lava lamp. That is a lamp which contains two liquids, which have more or less the same density, but which are unmixed. Maybe you have seen that, the lava lamp. So here we also have two layers, different composition, but with the same density, no density contrast, not seen seismologically. Well, this is one of the most shown, yeah.
As far as I know, the difference in the velocities of seismic waves arises by differences in stiffness and not in density, right?
No, also differences in density and differences in temperature. Yeah? Differences in viscosity, you mean that? Differences in viscosity could be seen by a technique that is called seismic scattering. Differences in temperature and differences in density can be seen by the normal seismic waves, and differences in temperature again by mantle tomography. But this can be compositionally different. But if there is no density contrast, then it would be hidden. But anyway, this is a boundary which is not seen. Yeah, it is just from in this model. Okay, let's go through the other models. There is some evidence. It's just from a new paper from the Bayreuth group. They made some experiments that this high pressure phase, it's called bridgmanite, but it's a kind of iron magnesium mineral. That under these pressures, the melt is denser than the solid. And from that, they argue that there is a magma ocean around the core. A magma ocean around the Earth core. Yeah? That could be the part beneath the D double prime layer. We are not quite sure what kind of material is in that, or how that is made up of. And there is also a model, the D double prime model, also from Hoffmann, Tolstikin and Hoffmann. It was developed, and it says that the material around the core consists of ancient subducted crust, of very early crust. The Earth had an early crust, but that is not seen anymore. Now it's destroyed. We can see it on the Moon. The Moon still has the old crust. The Earth doesn't have. And there was a heavy bombardment on the Earth's early crust, and that has caused an iron enrichment of this early crust. And they argued that that crust was quite heavy, quite dense, and was subducted down to the core mantle boundary. And that constitutes the presently visible D double prime. And that material is enriched. It is enriched because it is an early crust. So there we would have a source for enriched material. That is basically is an old model which was modified and so, and this is still one model which can explain quite part of the isotope feature, and still belongs to the layer cake. And the last layer cake model is a very elegant model from Bercovici and Carato. It's in some textbooks which said that may be the best model, but I'm not sure if it is really. But just to explain, it says that there must be material flow from the lower mantle to the upper mantle because so much material is subducted. And then when this material goes up, it's a passive upward flow. When the wachsleite is transformed into the olivine, then so much water is released because the wachsleite, the beta olivine, can contain up to 2% water. If that is true or not, if there is really so much water, is another question. But they argue that the water is released here, and then the water the water is released, and then a melt is formed, a melt layer. And this melt layer acts as a filter. All the material which comes up here, all the incompatible elements are released into the melt, and then the material gets depleted. Yeah, and so we come from a non-depleted into a depleted mantle, and that is the source of the MORPS. It's a completely different model, but it is Well, the main point against that model, in my opinion, is that it cannot really explain the isotopic differences which we see between the MORBs and the OIBs. Because this mechanism does not change the isotopes. It just changes the elements. Yeah? This filter here can keep the elements. And the other question, do we really have so much wet mantle material here that the Watzleite has 2% water? It is shown experimentally. Watzleite can contain 2% water. Olivine can't keep the water. So if there's water, the water is released, and the melt layer is about 10 kilometers thick here, could form. Here the melt layer doesn't prevent the material, because this material, the plume material, is too hot. It's about 200 degrees hotter, and then the Watzleite will not release the water, or doesn't contain so much water. So the plumes are allowed to penetrate this filter. That's why it's called the filter or water filter model. This is a comment on that from A.L. Hoffman. He wrote another paper only on that model. Yeah. But it's still in discussion. So, huh? The water, from here to here, it can't go up, because only here Watzleite is stable. Watzleite gets unstable here. It breaks down into olivine, and olivine cannot keep the water in the crystal lattice.
Then shouldn't
the water rise up. Further, the water, if it's released, it would give rise immediately to melting. So we would have a melt zone, and then it depends on the density of this melt zone, if this is stable or not. They argue that this melt zone is stable, and then it even gets deeper into the transition zone. Yeah, let me finish with the last one. I think this is already the last model. This is a model from the other type, the plum pudding model. By the way, this is a nice read here, this paper. It's an overview, and it also contains some of the mass balance calculation I showed you. Yeah, this model actually considers the mantle like it's shown here. So there is no layering in the mantle, and the compositional difference is just due to this material here, to the plums. And this material comes from the subducted material. In the mantle we have a process called convective steering. Convective steering, not complete mixing. And due to the convective steering we get these isolated blobs. And there is some evidence, but this is not seen by the tomography. The tomography has a resolution of about 400 to 600 kilometers. Only bodies like this you can see by mantle tomography. But by another method, by seismic scattering, you can see much smaller bodies. And there's evidence from seismic scattering that such bodies exist. Or at least there is some seismic scattering, and when you explain it, what can it be? What can be seismically scattered? Thermal anomalies, small bodies with different temperature is not possible. That would get equilibrated. It could be material of different viscosity, for instance. So maybe some relics of oceanic crust or other subducted material. And that would be more or less homogeneously distributed in the mantle. Yeah. Here are the mid-ocean ridges. Yeah, so the heterogeneities disappear here, more or less. The material is well mixed. And ocean islands, they could tap depleted or non-depleted or also enriched material. Yeah, this is the last model. Actually, the very last I found, just because it's an ongoing model from a group, Balmer et al. They just show the fact that the slabs may penetrate the discontinuity or may not. Both cases are considered here. So floating, they call it floating of the slab due to this clapeyron slope. And but this is also a whole mantle convection model actually. No? The whole mantle can convect, and we can see a moderate layering actually also. So it's a kind of hybrid model. Yeah, it's just the last one I found. They also explain some of the layering by unmixing of material. Yeah, this is a process like when you have oil and water unmixes. Some processes like this could happen in the mantle and give rise to some layering. So if this is better than the other models or can explain more, it's very difficult to say. I think all these models are interesting, and they are based on really strong arguments. But you also find some points which are difficult to explain. So I must leave it with that. And in the last, you can see some literature when you want to go in detail. This is where the models are from, and some overview papers. Some good reading, I think, for that. Okay, then. Do you have any questions about that? If some points are unclear, next week we could continue with that. If not, we would continue with a completely different topic, with the continental crust, formation of the continental crust. Actually, what we did not do, you might have seen that we didn't talk about the evolution of the mantle. Yeah, we only looked at the present day picture. If you would look at the evolution to time, that would be even more difficult. Look at the old Archean rocks and the isotopic signatures. We mainly looked at the present day stage of the mantle. And when we look at the continental crust, we will go through time. We will start with a very early crust formation and look at different processes of crust formation during time. Yeah.